let's have a look. Okay, there's a small problem here. Okay, good. So we are looking at page 42, number 7. So page 42, number 7, what are we told? We are told that we have a log which is floating swiftly. Let me actually switch. So we have a log that is floating swiftly on moving water. A stone is dropped from rest from a 75-meter bridge and lands on the log as it passes under the bridge. If the log moves with constant speed of 5 meters per second, what is the horizontal distance between the log and the bridge when the stone is released? So here I've got the diagram. What we have is we have a bridge, and there's someone here at the bridge, and they drop a stone, and the height of the bridge is 75 meters. If they drop the stone, then we know that the initial speed for the stone is 0, and we have a log at the same time which is traveling through. So under the bridge there's some water, and the log is just traveling towards the right in this case, at 5 meters per second, which is constant. So for the log we can just use S is equals to Vt, whereas for the stone we have G, and I've chosen down as positive for my direction. And as soon as the stone hits the water, we are told that it hits the log, so it exactly hits the log. The height is 75, and we want to know what is this distance here that the log traveled to reach the stone. Okay, so let's have a look. So just to redraw the diagram, so there's our bridge. Under here there's water. We have a log over here, and at the bridge someone drops a stone. The height of the bridge H is 75 meters. Okay, and we said that the initial speed is 0. I've chosen down as positive for the log, and I've chosen towards the right as positive, for the log is towards the right, and for the stone it's down. So we know G for the stone, it's positive, which is 9.8. So we need to find the time, because S is equals to Vt. We know the speed of the log. We just need the time to find the distance between the log and the bridge. I mean that the log traveled before it actually reached the stone. So here we have H, we have Vi, and we have G. We want T. There's no Vf, so the equation of motion that we are going to use for the stone, so this is for the stone, is I've called it H, so H is equals to Vit plus 1/2 Gt squared. Okay, so Vi is 0, so that term is just 0. We are looking for T, so we need to multiply or divide by half G. So if we do that, we find T squared equals H, the 2 goes on top over G, so that means T is equals to the square root of 2H over G. Substituting the values, we find T is equals to square root 2H is 75 and G is 9.8. So if we now calculate this, what one will find is, let me just check, 3.91 seconds. Okay, so one should find 3.91 seconds. So that's the time it took for the stone to reach the log, but that's the same time that the log took to go from here to reach the stone. Okay, so that's the same time T. So then we learn S is equals to Vt. V is 5, and T we've just calculated, we said 3.91. So multiplying these two, one finds that S is just 19, not 19. Yeah, so S is 19.56 meters. Okay, so that solves question number 7. Okay, so now which question? So now we are looking at number 6. Okay, so let's just switch and make sure that we shift the book so that you can see which question we are doing. So we're looking at number 6, and number 6 tells us we have two balls which are dropped to the ground from different heights. This is page 41, and one is dropped 1.5 seconds after the other, and they both strike the ground at the same time, which is 5 seconds after the first one is dropped. Calculate from which height was each ball dropped. So that's another question. It's not too difficult, so we are looking at page 41, number 6. Okay, so page 41, number 6, what do we have? There's our ground. We have a stone, let's call it stone A, and it's dropped at some height. Let's call it height up for large. Another stone is dropped at a smaller height, which we'll call H down for small. Let's call that one B. So we will choose down as positive, which is the direction of motion. That means our G is positive 9.8 meters per second squared. These are dropped, so VI for A is equals to 0 and VI for B is equals to 0. We know that it takes 5 seconds for the first ball, which is the ball at the higher height. So then TA is equals to 5 seconds. But for B, B is released 1.5 seconds later, so TB takes 1.5 seconds less. So it's 5 minus 1.5, which is 3.5 seconds. Okay, so the time it takes for B to reach the ground. And we'd like to find H down and H up, so the height of B and the height of A. So the height of A is given by VI T plus 1/2 GT squared, because we don't have the final speeds for both of them. So then VI is 0, so that term just dies. So then we just have 1/2 9.8, and T for A is 5 seconds squared. So multiplying these out, you get HA is 122.5 meters. Okay, what about B? So for B, HB is the same equation. We also don't have the final speed, so VIT plus 1/2 T squared times G. So TB here I should have written TA for the A, and here VI is 0, so we just substitute. We have 1/2. The time for B is 3.5, so 3.5 squared times 9.8. Multiplying these two out, we find HB is equals to, let me just check, 60.0, so that's a 0, 60.025 meters. Okay, so those are the heights of the two objects, or the two balls. Okay, so that's number 6. Now we will skip number 5 and go to number 4. So number 4 says a train takes 25 seconds to pass through a town with constant speed. So let's just stop there and record the information. I'm trying to get a new page. Okay, so let's remove that. So new page. So we are on page 41. We're looking at problem number 4. Okay, so a train goes through town. So through town, the information that is given is that it travels at constant speed. So constant speed means we can use S is equals to VT. And let me just check. It takes 25 seconds to pass through town at a constant speed of 16 meters per second. So T is equals to 25 seconds and v is equals to 16 meters per second. We choose positive as the direction of motion, so direction of motion, and we can easily see that we can find the distance for through town using s is equals to vt. Okay, so let's continue reading. And then we are also told after leaving the town, the train accelerates at 0.33 to reach a final speed of 35 meters per second. So after leaving town, so let's just say after town, accelerates, so a is positive, a is equals to plus 0.33 meters per square second. It's positive because also the final speed is larger than the initial speed, so the final speed is 35 meters per second. If before it goes after town it was moving at 16, that means the initial speed was just 16 meters per second, second, not second square. So let's just remove that. Okay, so we're looking for the distance. So the question is how far did the train travel during this time? Okay, so to calculate how far the train traveled, we are looking for the distance s. So you can see that there's two parts. So let's call this S1 and call this one S2. So then S1 is Vt, which is 16 times 25, which is just 400 meters. Okay, so that's S1. Then S2 is equals to Vit plus 1/2. Oh, we don't have t, so the equation we are going to use is Vf squared equals Vi squared plus 2as, and we're looking for s, so let's take Vi to the other side and divide by 2a, so we get Vf squared minus Vi squared over 2a equals the s that we're looking for. So s is equals to Vf is 35, so 35 squared minus 16 squared over 2 times 0.33. Okay, so if you plug those in, what you find is S2, so let's just make sure that that is S2. S2 is 1468.2 meters. So then the total distance that the train travels, S is equals to, so S total is equals to S1 plus S2, which is just, if you add this distance with 400, you get 1868.2 meters. Okay, so that's part A of the problem. So we have solved part A. Part B, we are being asked what is the train's average speed during the trip. So what we need to do is we need to first find the average speed through town, find the average speed after town, and then the average speed for both of these trips. Okay, so for through town, the average speed is just V. So V is equals to V average, because it's a constant speed, so which is just 16 meters per second. And then after town, the average speed is found by adding the final and the initial and dividing by 2. So V average is 1/2 Vf plus Vi. The same way that if you've got two people, one weighing 100 kilograms, another weighing 50, you want to know their average mass. Maybe these are rugby players in the same team. Then you would just add 100 to 50 and divide by 2 to get 75. So it's the same concept. We take the initial speed, add the final speed, divide by 2. That's the average speed for the trip. So if you do that, what you will find is the average speed is just 25.5 meters per second. So Vf, just remember, is 35, Vi is 16. So adding these two, dividing by 2, you get 25 meters per second. So now we need the average for the whole trip, and the average for the whole trip is just adding the average for trip 1 to the average for trip 2, divide by 2. So V average in total is just V1 average plus V2 average over 2. So V1 average is this here, so that's just 16, and then the average speed for the second trip is this one here, so that's 25.5 over 2. Then our average speed for the whole trip is just, if you add those two and divide by 2, which is 20.75 meters per second. Okay, so that completes question 4, and then now I would like to look at one more problem from the problems that we cover in lectures, and that's question 3. So for question 3, we have Carl Lewis, who's an Olympic runner, who set a world record for the 100-meter run with a time of 9.86. So this guy was very quick. He covered 100 meters in 9.86, and then after reaching the finish line, Lewis walked directly back to his starting point in 90.9 seconds. And what we want to know is to calculate the average speed for the 200 meters and to calculate the magnitude of his average velocity for the same 200 meters. Okay, so let's just open a new page. So what we want to do is to realize, so we are looking at page 41, number 3. Okay, so what we have here is we have a runner, Carl Lewis. He covers 100 meters, so the distance here is 100 meters. So first he runs the 100 meters in a race against other people, and it takes him 9.86 seconds. Okay, so that's the time it takes him, and that's a world record. So we'll just say time 1 for the forward run. And then afterwards he's tired and he walks back. So now he walks back and it takes him time 2, which is 90.9 seconds to cover the same distance. So now you can see that for the forward trip, which is over there, let's use blue again. So for the forward trip, we have S is equals to V average for this trip. So we want the average speed for this trip. So S is Vt because we are using average speed. So average times T. If you're not happy with this, just think of this as 1/2 Vi plus Vf times T. So 1/2 Vi and Vf is my average speed. So even though the racer will be accelerating, we don't worry about that. We just want the average speed, which is given by this equation of motion. So for this, I'm going to choose positive to be the direction of motion, well, not direction of motion, but positive to be for the run. That means going back, I have a negative. Okay, so we learn that V average equals S over T, which is 100 meters over 9.86 seconds. And if you calculate that, what you will find is his average speed is 10.14 meters per second. Average velocity for that trip, the same trip has direction, so it's gonna be 10.14 meters per second east. Okay, and then now he goes back and he walks. So for walking back, we have S is equals to V average again, so that's the red trip going back, times T, and that means the average speed is equals to S over T, and S is the same, so 100 meters, and the time it takes now is 90.9 seconds. If you multiply those two or divide those two, what you will find is the final answer for that duration is 1.10 meters per second, and that means the average velocity for the second trip is just 1.10 meters per second west. Okay, so then the question is calculate the magnitude of the average speed for the 200 meters. So the first part, we are interested in the average speed. So then remember that the average speed is just the speed for the one trip, which is forward, plus the speed for going back divided by 2. So average speed for the whole trip is just equal to the blue speed over here, so V, not velocity speed, so V average here, and then I need to add the red speed, so V average from here, and divide by 2. So it's the sum of those two over 2. If I do that, what I find is I have 10.14, so 10.14 plus 1.1, so 1.10 over 2. Then I learn that for the whole 200 meters, the average is just, let me just see. Okay, so I haven't calculated it here. I'm just going to look for a calculator. Okay, so whilst I'm looking for my calculator, I just want to say that there's another way of finding this average speed. You can just say for the whole trip, the average speed is the total distance over the total time. Okay, so the total distance was 200 meters, and the total time is okay, so I'm being helped with the calculator. Okay, so there we go. Okay, cool, thanks. So what we have is we want 10.14, and to that we add 1.1, and we want to divide by 2. So if I divide by 2, I get 5.62. So my answer is 5.62 meters per second. And I just said there's another way, so you can take the whole distance, divide by the total time, which is 90.9 plus 9.86. So just to check that our answer corresponds. So what we have now is we want to add 90.9 to 9.86. Okay, so that's 100 point. So let's just record that number. That's 100.76 seconds. So what I want to do now is take 200 and divide by our 100.76. Okay, so they don't give the same answer. That's odd. We get 1.98. Okay, I will check this, and then in the next lecture I will just say which, but I think this is the correct answer and what was the problem with the other one. Okay, so now we go to the second part of the problem, which is part B. We want the magnitude of the average velocity, and then we are done for this lecture. So we want the magnitude of the average velocity. So the magnitude of the average velocity is not very difficult to find. So just remember that now we have directions. Just a reminder that we had for the forward trip, which was where he was sprinting, V average velocity was 10.1 let's just 10.14 meters per second, and this was east. And then the return trip, the average velocity was 1.10 meters per second, and this is west. Okay, so if now I want the average velocity for the whole trip, so for the whole trip I just need to add for the forward trip the average velocity to the average velocity for the return trip and divide by 2. So if I add those two and divide by 2, just remember that these are vectors, so east is what we said was positive, that means west is negative. So this is actually 10.14, it's a plus minus 1.10 over 2. So if I add those two in that fashion, what I find is my average velocity for the whole trip is, so I want 10.14 and to subtract 1.10 for this trip, which is 9.04, and to divide by 2, and we have 4. Okay, so we have 4 point, let's just double check, 4.52. Okay, so it's 4.52 and it's a plus meters per second, which means it's 4.52 meters per second east. Okay, so that's the final answer. And actually I've just realized what's wrong with the other equation, because even here, remember that average velocity would be given by the displacement and not the distance over the total time. The displacement in this case is 0. So if the displacement is 0, that means the average velocity is 0. But that's not the case, because the person ran at a different speed going forward and ran at a slower pace coming back. So this formula gives us the wrong answer in this case. So that is why when we tried to calculate earlier over here, we got the wrong answer. Okay, so you need to use the speeds themselves to get the correct answer. Okay, so that solves why this gave us a wrong answer. Okay, so that's the end of the lecture. I would encourage that you do your tutorials, and then I will send my solutions via Blackboard, and you can look them up. Okay, thanks. That's the end of this section.